Didn't see you there. Isn't nature amazing? It's a beautiful day, 75 degrees in the middle of August. We're here in Rock Creek Park in Washington, D.C. Why are we so lucky to have such great weather? Whether you believe me or not, weather and climate events that happen in other places around the world affect the area that you live in, including as far north as the Arctic. In fact, most scientists and meteorologists agree that the weather and climate events taking place in the Arctic today are going to have implications for the rest of the world.
The Arctic tundra is perhaps the coldest and harshest of the Earth's biomes. A biome is defined as the world's major communities classified according to the predominant vegetation and characterized by adaptations of organisms to that particular environment. The word tundra comes from the Finnish word tunturia, meaning treeless plain, which, as you know from the last video, trees cannot grow in the Arctic. The climate is cold and windy, with scant rainfall. Tundras have an extremely low climate, low biotic diversity, or low diversity of living organisms, such as plants and animals, and have very simple vegetation that is adapted to sweeping winds and disturbances of the soil. Plants are short and grouped together to resist the cold temperatures and are protected by the snow during the winter. They can carry out photosynthesis at low temperatures and low light intensities. Some of these plants include low shrubs, sedges, reindeer mosses, liverworts and grasses, 400 varieties of flowers, and different types of lichens. Animals are adapted to handle long, cold winters and breed and raise young quickly in the summer. Animals such as mammals and birds also have additional insulation from fat because of the cold. Some of these animals include migratory birds, mammals such as muskox, polar bears, lemmings, Arctic foxes, walruses, beluga whales, seals, and narwhals. And there's also fish like cod and salmon. According to the National Snow and Data Ice Center, when we discuss climate, we are talking about weather of a certain place averaged over a period of time, usually about 30 years. Studying the climate tells us about the normal weather for a region, as well as the range of weather extremes for that location being examined. When we discuss weather, we are referring to the day-to-day state of the atmosphere and its short-term variation in minutes to weeks. People generally think of weather as the combination of temperature, humidity, precipitation, cloudiness, visibility, and wind. The Arctic is a unique place for both weather and climate, as you might have guessed. Sunlight is extremely important to the region. North of the Arctic Circle, in the summers, the sun shines around the clock, bringing warmth and light. In the winter, the sun disappears, leaving the region dark and cold. Weather and climate patterns in the Arctic can influence weather and climate around the world, particularly in the northern hemisphere. This is because the Arctic region acts like a heat sink or refrigerator for the Earth. A heat sink refers to the process in which energy is removed from the atmosphere in the form of heat. The Arctic loses more heat to space than it absorbs from the sun, cooling off the rest of the planet. When warm air and water from tropical and temperate regions move into the Arctic, it provides a place for the heat to escape. Some weather patterns do originate in the Arctic. These weather systems that are formed in the Arctic do move south and can bring cold temperatures and snow, including the polar vortex in January of this year that hit the northeast U.S. Scientists first started to see changes in the Arctic climate in the 1970s and 1980s. Over the past 30 years, it has warmed more than any other region on Earth, and most scientists agree that Arctic weather and climate are changing because of human-caused or anthropogenic climate change. Arctic warming is causing changes to sea ice, snow cover, and the extent of permafrost. In the first half of 2010, air temperatures in the Arctic were 4 degrees Celsius warmer than the 1968 to 1996 reference period, according to the NOAA. Satellite data show that over the past 30 years, Arctic sea ice cover has declined by 30% in September, the month that marks the end of the summer melt season. Satellite data also show that snow cover over land in the Arctic has decreased and glaciers in Greenland and northern Canada are retreating. In addition, ground in the Arctic has started to thaw out. Arctic scientists and researchers are worried about changes in the Arctic because it could lead to positive feedback effects that spur further warming, also known as Arctic amplification. For instance, when white sea ice melts in the summer, areas of dark open water are exposed, which can absorb more heat from the sun, leading to a reduction in albedo. That extra heat then helps melt even more ice. Albedo is a non-dimensional, unitless quality that indicates how well a surface reflects solar energy. As permafrost thaws, plants and animals that were frozen in the ground begin to decay. When they decay, they release carbon dioxide and methane back to the atmosphere that contributes to further warming. Black carbon, or soot, is released during the incomplete combustion of fossil fuels, biofuels, and biomass burning, which can come from agricultural burning, wildfires, on-road diesel vehicles, residential burning, off-road diesel, and industrial combustion. Black carbon darkens the surface of the Arctic and decreases albedo, which leads to the absorption of solar radiation and faster melting rates. We will now discuss some of these major positive feedback loops. The first is increased atmospheric CO2, which will change the composition of the plant communities in the Arctic. Some will thrive and others will die out. The second positive feedback loop is increased temperatures, which will also change plant communities, but also create longer seasons without snow, the possibility of more wildfires, and increased invasive species. Already, more southern animals like the red fox have moved into the tundra. The red fox is now competing with the Arctic fox for food and territory, and the long-term impacts on the sensitive Arctic fox is unknown. The loss of some plants will affect fish and wildlife in ways that are difficult to foresee. The third feedback loop is melting snow and ice. Thawing soil ice changes hydrology, which will lead to terrain instability and vegetation change as described before. This will lead to the thawing of frozen organic material stored in tundra soils, which will release huge amounts of greenhouse gases into the atmosphere. Glacier mass loss has also been observed across the Arctic. Some glaciers are projected to completely disappear in the coming decades. The fourth and fifth feedback loops are related to changing precipitation patterns. More winter thaws and rain on snow will harden the snowpack, hampering mammal migrations and foraging. More extreme rain and weather events will cause landslides, erosion, and disrupt surface drainage patterns. The last feedback loop is that drier conditions and even drought are also more likely. This will lead to a reduction in the sensitive coastal plain wetlands, making it difficult for fish to be able to pass in streams. So what does climate change in the Arctic mean for the rest of the world? Amplification of global warming in the Arctic will have fundamental impacts on northern hemisphere weather and climate. The second impact is that the global ocean circulation system will change under the strong influence of Arctic warming. The third is that the loss of ice from the Greenland ice sheet has already increased and will contribute substantially to global sea level rise. Arctic marine systems currently provide a substantial carbon sink, but the continuation of this depends critically on Arctic climate change impacts on ice, freshwater inputs, and ocean acidification. Arctic terrestrial ecosystems will continue to absorb carbon, but warming and changes in surface hydrology will cause a far greater release of carbon into the Earth's atmosphere. And lastly, the degradation of Arctic subsea permafrost is already releasing methane from the massive, frozen, undersea carbon pool, and more is expected with further warming.